Welcome to our deep dive, you know, into this fascinating world of quantum error correction. We're going to be looking at an essay today
Okay.
by Jörg O. Schneeppert
Okay.
called Fehlerkorrektur,
Yeah.
Stabilität für Quantencomputer.
Mm.
It's in German, of course.
Right.
And you've probably heard the buzz about these quantum computers. They're these machines
Yeah.
that use these kind of bizarre, almost ideas from quantum mechanics to solve problems
Yeah.
that regular computers would take
Right.
like forever to do.
Absolutely.
Like breaking codes,
Yeah.
making new materials, simulating molecules.
Yeah.
But here's the thing. They're really prone to errors.
Yeah.
Like super
sensitive.
sensitive. Yeah.
Yeah.
It's like,
A house of cards.
yeah, house of cards on a trampoline.
Yes, exactly.
With any little
nudge.
yeah, just messes the whole thing up.
It's true.
So that's where quantum error correction comes in. It's not just like an optional feature.
No, not at all. No.
It's like the foundation
It is the foundation. Yeah.
that it's all built on. And Jörg O. Schneeppert, in his essay,
Yeah.
really stresses this point.
He does. Yeah.
So let's dive into why these errors are such a big deal
Okay.
in quantum computing.
Yeah.
So we know that these machines operate on principles like superposition and entanglement.
Yeah.
Can you just give us like a quick
Excellent.
explanation of why those
Yeah.
are so crucial to
Sure.
needing this error correction?
Absolutely. So superposition basically means you have a regular computer bit, and it can be either a 0 or a 1.
Right.
But a qubit, which is the quantum version, can be a 0, a 1, or both at the same time.
Wow.
And that's
So it's not just,
wild.
yeah, it's not just more possibilities. It's like a totally,
It's a fundamentally different way.
yeah, different way of like representing information.
Totally.
Yeah.
Wow. Okay. So,
And then you've got entangled.
which is even weirder. So imagine like two of these coins that are spinning,
Mhm.
and if one lands on heads, the other one instantly flips to tails no matter how far apart they are.
Oh, wow.
That's entanglement. It's like there's spooky action at a distance.
Right.
But this connection is what gives them so much power, but it also makes them super sensitive to any kind of interference.
Right. And Schneeppert calls this decoherence.
Right. He does.
It's like if you have these two coins spinning,
Yeah.
and someone comes along and like,
A gust of wind or something.
yeah, and messes it
Yeah.
up.
It bumps it.
So it's like
yeah.
those qubits get forced into one state or the other
Exactly.
when they shouldn't be
Prematurely.
because of like noise, like temperature,
Yeah. Noise, temperatures, vibrations, anything.
electromagnetic fields.
Anything. Yeah.
Wow. So unlike our laptops,
Right.
that can help a little bit of,
You can drop them and
yeah, rough handling.
you're fine.
Quantum computers are like,
They need like a perfect environment.
yeah,
Yeah.
they're very sensitive.
Yeah.
That's why error correction is
So important.
so important.
Yeah.
So, but fixing errors in a quantum computer
Yeah.
isn't like fixing errors in a,
In a regular computer?
no, in a regular computer.
It's a whole different ball game because
Yeah.
we can't just make copies of the information
Right.
because of something called the no cloning theorem.
The what?
No cloning theorem.
Okay.
You can't just copy a qubit.
Wow.
So that's a big challenge.
So how do you,
Schneeppert talks about this a lot in the essay.
yeah, how do you even begin to protect information if you can't back it up?
Right. Yeah.
It's like saying you can't photocopy a dream.
Yes, exactly.
So how do you,
That's a great analogy.
yeah, how do you even do it?
So this is where quantum error correction comes in.
Okay.
It's brilliant.
Okay.
It's really clever. So Schneeppert talks about Peter Shor
Okay.
and his solution.
Oh, Shor's algorithm.
Shor's code, yeah, same guy.
Wow.
So instead of copying a qubit, imagine you're spreading the information out
Okay.
across 9 physical qubits.
Okay, so you're not copying it. You're like
You're encoding it.
encoding it
Yeah,
across a bunch of different,
across a bunch of different ones.
okay.
So even if a few of them mess up,
Uh-huh.
you can still get the original information back.
Okay, so it's not about fixing errors. It's about
It's about preventing them in a way.
preventing, yeah.
Yeah. Yeah.
Okay. In
And
short,
so Shor's code was huge.
Yeah.
Because it showed that it was possible
right.
in theory.
In theory.
Yeah.
Okay.
So it's like building this fortress around the information
right.
to protect it.
But how does that actually,
How does it actually work?
yeah, how do you build a fortress around information?
Right.
What are the
Good.
mechanisms
Yeah.
that you use to do that?
So Schneeppert mentions stabilizer codes,
Okay.
which are basically like a set of operations you
Yeah.
apply to these qubits that can tell you if there's an error without actually looking at the information itself.
So it's like you're checking for cracks in the foundation
Yeah, exactly.
without disturbing it.
Yeah, without, like, destroying the house.
Right. Yeah, that's a good way to put it.
And then Schneepat also mentions
Yeah.
topological codes.
Yeah.
What are those?
Those are another approach
Okay.
where you arrange the qubits in a specific way
Yeah.
that makes them even more resistant to errors.
Wow.
It's like weaving a net
Oh, okay.
to catch the errors. So that
Okay.
even if there's like a little snag,
The
it's still...
information is still protected.
The information's still there.
Okay. So how close are we to actually
Good question.
building these fortresses in the real world?
Right, that's the big question.
Yeah.
Well, building these fortresses in real systems,
Yeah.
it's tough.
Yeah.
It's a huge task.
Yeah.
You need like hundreds or thousands of physical qubits
Oh, wow.
to make just one.
To represent one reliable logical qubit.
Wow, okay.
So as you add more qubits, it gets harder.
Exponentially harder.
Yeah, it's way harder.
Okay, so are we anywhere close?
Well, there have been some successes,
Okay.
especially with something called surface codes,
Okay.
which is a type of topological code
Okay.
that works well with superconducting qubits,
Uh-huh.
which are one of the ways we're building
Right.
quantum computers these days. So
Right.
groups like IBM and Google,
Okay.
they've shown
They've done it
they've done it on a small scale.
on a small scale. Okay.
Yeah.
So we're starting to see those blueprints become real structures.
We are, yeah.
That's exciting.
It's really exciting.
But it sounds like we're,
Early stages.
yeah, still in the early stages.
Yeah.
So what are some of the things that people are thinking about to push?
Well, AI,
Fighting.
artificial intelligence, is
Yeah.
a big one.
Okay.
People are really excited about that.
How so?
Well, imagine AI that can sift through all this data
Uh-huh.
coming from these quantum computers
Yeah.
and learn how to diagnose and fix errors.
Wow.
Even predict them before they happen.
Wow, that's like,
Like a quantum mechanic.
yeah, a quantum
On a
mechanic
computer.
that's constantly monitoring it
Yeah, that's a great way to put it.
and making sure it's running smoothly.
Yeah.
That sounds like,
It sounds futuristic,
yeah, it sounds very
but it's possible.
far out.
Yeah, and Schneepat talks about this.
It does.
He does. He
Yeah.
calls it adaptive error correction.
Adaptive error correction.
Yeah,
So it's like a self-healing system
exactly.
that's learning as
Yeah.
it goes.
It's constantly learning.
Wow. So what's the ultimate goal here? Is it to have like error-free quantum computing?
That's the dream.
Okay.
Yeah, that's the ultimate goal.
A world where these
Temperamental artists.
these temperamental artists become like reliable workhorses
Yes, exactly.
capable of solving,
That's a great way to put it.
yeah, any problem we throw at them. So how realistic is that?
Well, to be honest, it's probably decades away,
Oh, wow.
but we're making progress.
Okay.
Every little step
Every little step.
brings us closer.
Okay.
And Schneepat reminds us
Okay.
that the field is moving really fast.
Yeah.
We're just scratching the surface.
Okay, so let's just take a step back
Okay.
and recap what we've learned so far
Sure.
from this essay by Schneepat.
Yeah.
First of all, quantum error correction.
It's not optional.
It's essential.
Absolutely. It's like,
The foundation of a skyscraper.
yeah,
You can't
you
build
can't build anything without it.
anything without it.
Yeah,
And we've learned that it's like
totally different
totally different.
from classical error correction.
Yeah.
It's not about making copies. It's about
It's about encoding
encoding the information
Yeah.
in a clever way.
in a clever way. Yeah.
And we've explored some of those approaches, like Shor's code,
Mm.
stabilizer codes, topological codes. Yeah.
All these different ways of building these
Those are just
fortresses around the information.
Yeah,
But as you said, there's still a long way to go
there is. Yeah.
before those temperamental artists
Yeah.
become reliable
Yeah.
workhorses.
Yeah.
But there's a lot of exciting stuff happening
Oh, yeah.
with AI
Yeah, that's the big thing.
and machine learning.
Absolutely.
So for our listener, why should they care about this?
That's a good question.
Why does it matter?
If those qubits get messed up,
Yeah.
right?
Why should they care?
Because the success of quantum computing depends on it.
Really?
Yeah.
Okay.
All those amazing breakthroughs we keep hearing about, like new drugs,
Yeah.
new materials,
Right.
super powerful AI,
Yeah.
that's all relying on
On getting this right.
getting this right. Yeah.
Wow. So in a way, error correction is kind of like the unsung hero.
It is. It's the behind the scenes worker,
Yeah.
making sure everything works.
You know, making sure that those temperamental artists
Right.
can do their thing.
Exactly.
So, and
Yeah.
as Schneepat says in his essay,
Yeah.
the field is
Moving fast.
rapidly evolving.
Yeah.
We're on the cusp
We are.
of this new era of computing.
Yeah.
And error correction is going to be
Front and center.
right at the front.
Absolutely.
So it's like we're explorers charting uncharted territory, and there's going to be a lot of
surprises, discoveries along the way.
Totally, yeah.
That's what makes it so exciting.
That's what makes it fun.
Yeah.
Yeah.
So in our next segment, we're going to delve even deeper into the future of quantum error correction.
Sounds good.
We'll explore some of the cutting-edge advancements that could unlock the full potential of this technology. Stay tuned. I will. Picking up where we left off, I think it's important to stress that it's not just about making these machines more reliable. It's about unlocking their full potential. Like to tackle problems that classical computers just can't even touch.
Right. It's like the difference between having like a basic calculator and a supercomputer that can simulate the entire universe.
That's a perfect analogy.
Yeah.
Yeah, and Schneepat in his essay really highlights this.
So how would error-free quantum computing like actually revolutionize those fields?
Okay, so imagine being able to simulate like a molecule at the atomic level with perfect accuracy.
Right.
Even the best computers we have today really struggle with that.
Yeah.
But a fault-tolerant quantum computer who could do it easily?
So we could design drugs that are like super precise.
Exactly.
Targeting specific
side effects.
Diseases, no side effects.
Yeah, like that sounds incredible.
It sounds like sci-fi.
Yeah. But it's a real possibility. Wow. And in materials science, we could engineer like totally new materials that are stronger, lighter, better conductors.
Yeah.
Do things we can't even imagine right now.
So this would revolutionize everything.
Everything.
From energy to like
aerospace, yeah.
Yeah, it's crazy.
It's mind-boggling.
It is, yeah.
The possibilities.
And that's not even mentioning AI.
Oh, right, yeah.
Schneepat talks about that too.
You're saying that error-free quantum computing could revolutionize AI itself.
Exactly.
Oh, wow.
It could like supercharge machine learning.
Right.
So you'd have AI that can understand language.
Yeah.
Make really complex decisions.
Right.
Like a human.
Like it could actually think like a human.
Almost, yeah.
Wow.
And predict things like the climate.
Wow, okay.
With amazing accuracy.
So we're talking about AI that can't just like solve problems. It could actually understand things.
Understand, yeah.
On a deeper level.
It's a possibility.
Wow. And Schneepat
doesn't rule it out.
Yeah, he doesn't rule it out. Okay.
He thinks it could lead to all sorts of breakthroughs.
Right.
Personalized medicine, finance, even physics.
It's amazing to think that these fields that seem so different could like come together.
They could, yeah.
And like boost each other.
It's all connected.
Wow. Okay, but let's be realistic for a second.
Oh.
Schneepat says that near-perfect error correction is like a really long way off.
It is, yeah.
Decades away.
Probably.
So what are like the biggest hurdles that we still have to overcome?
Well, one of the biggest is just the complexity of scaling this up to millions or billions of qubits.
Right.
It's not just about fixing like one error at a time.
Yeah.
It's about managing this whole web of entanglement, which gets really messy.
Yeah, it's like keeping a billion butterflies flying in formation.
Perfect analogy.
And even if we do achieve like perfect error correction,
even then,
it's still
rapidly evolving field.
Yeah.
So there might be like
new challenges.
Totally new challenges.
We haven't even thought of yet that we'll have to deal with.
So what are some of the key questions that we need to be thinking about as we move forward?
Well, one is, how do we measure progress?
Oh.
Because right now, there are so many different groups doing so many different things.
Yeah.
So we need some way to figure out...
which ones are working.
Yeah. Which ones are actually working.
Okay.
And which ones are just dead ends.
Right. So it's not just about building...
bigger computers.
Bigger quantum computers.
It's about making sure we're on the right track.
We're going in the right direction.
Yeah.
Okay. And as we make progress towards these more powerful computers, we need to think about
the big picture,
the societal implications.
Yeah, the ethical implication.
What kind of implications are we talking about?
Well, one is cybersecurity.
Okay.
Because if quantum computers get powerful enough, they could break all the encryption we use today.
Right.
So we need to start thinking about
new ways.
Yeah, quantum-resistant encryption.
Right, to protect ourselves.
Exactly.
Because it's like we're building this...
bridge.
Yeah, this bridge to the future.
Yeah.
But we need to make sure that it's secure.
Right.
And that everyone has access to it.
That's a really good point.
Yeah.
It needs to be equitable. for everyone.
So it's not just about the technological advancements.
Yeah.
It's about making sure that they
benefit everyone.
Benefit humanity as a whole.
And don't create new problems.
Yeah.
That's what Schnepphat is saying.
Right. So we need to proceed with caution.
With caution, yeah.
But also with, like...
excitement.
Excitement.
Yeah. It's a delicate balance.
Yeah, because it's a really powerful technology.
It is.
Yeah.
Super powerful.
It's important to use it wisely.
Yeah.
So these are conversations that we need to be having now.
Right now.
Not later.
And not later.
As we go further down this path.
Okay.
The future is still being written.
It is.
It's up to all of us to shape it.
Well said. Welcome back to our final segment on this deep dive into quantum error correction. You know, we've talked about the theory, the potential impact, all that stuff. Now, let's look to the future. Like, what are some of the cool things?
Yeah, the cutting edge.
Yeah, the cutting edge stuff that could get us closer to this dream of error-free quantum computing.
Right.
Schnepphat mentions some exciting possibilities in his essay.
Yeah, he does.
What are some of those?
Well, one thing that's really interesting is what he calls hardware-aware error correction.
Hardware-aware.
So basically, it's like tailoring the error correction codes to the specific hardware you're using.
So it's not like a one-size-fits-all.
No, it's more like a bespoke suit.
Oh, okay.
Yeah, you're customizing it.
So you're taking into account the specific...
quirks.
Yeah, quirks of
each machine.
Yeah, quantum computer.
Yeah, exactly.
So like the connectivity between the qubits, right? The types of errors that are most likely...
How fast you can perform operations.
All that stuff, yeah.
Wow, so it's really about like understanding the personality...
The personality, yeah.
...of each quantum computer.
Yeah, each one is different.
Wow, and Schnepphat says that this approach is already leading to like real improvements.
Better performance, more reliability.
Wow, that's great.
It's really promising.
Yeah, but it's not just about optimizing for existing hardware, right?
No, there's also new types of qubits.
Right, like topological qubits, which we talked about earlier.
The ones that are like knots.
Yeah, the knots.
Yeah, so they store information in a way that's way less sensitive to noise.
It's like writing a message in the clouds.
Oh, I like that.
Yeah, a few gusts of wind might mess it up a little bit, but the message is still there.
Yeah, that's a good way to think about it.
Yeah, so topological qubits are still...
Early days.
Early stages, yeah.
But they have huge potential for building these fault-tolerant computers.
That are just inherently...
robust.
Robust.
Yeah.
So we've talked a lot about how AI can be used to help with error correction. Like that quantum mechanic analogy.
Right.
But Schnepphat takes it a step further.
He does.
He talks about AI becoming like...
Part of the process.
Yeah, a part of the quantum computer itself.
Yeah, like baked in.
Can you explain what he means by that?
So he's imagining like a hybrid system.
Okay.
Where AI is working together with the quantum circuits.
So it's not just helping to manage errors. It's actually like...
Participating in the computation.
Participating, yeah, guiding it.
Making decisions.
Wow, so it's like a co-pilot.
A co-pilot.
For the quantum computer.
Yeah, that's a good analogy.
That's constantly adjusting and like anticipating problems.
Exactly.
Wow, that's a really cool idea.
It's pretty mind-blowing.
Yeah, but as we get into this territory, you know, we have to think about...
The implications.
Yeah, the societal impact.
The ethical question.
Right. And Schnepphat acknowledges this in his essay.
He does. He's very aware of those issues.
Yeah, because as we push the boundaries...
Of quantum computing.
Of quantum computing and AI.
And AI.
Yeah. We have to be mindful of, you know...
How it's used.
How it's used.
Yeah, who has access.
Making sure it's used for good.
Right, for the benefit of humanity.
A big responsibility.
It is a huge responsibility.
And it's not just on scientists and engineers.
It's on everyone.
Yeah, policymakers.
Citizens.
Everyone has a role to play.
Yeah, we all need to be part of the conversation.
Well, we've learned a lot today about quantum error correction.
We have.
It's been a fascinating journey.
It has.
From the theoretical foundations to the potential impacts to the ethical considerations.
It's a complex topic.
Yeah. But hopefully we've shown that it's a crucial piece of the puzzle.
Absolutely.
For unlocking the power of quantum computing.
It's the key.
Yeah, and Schnepphat reminds us that the field is
rapidly evolving.
Yeah, rapidly evolving. Yeah. So there's a lot more to come.
Oh, yeah, we're just getting started.
So for you, our listener, we hope this deep dive has not only explained...
Demystified.
Yeah, demystified this complex topic, but also made you excited.
Curious.
Yeah, curious about the future of computing.
Because it's going to be wild.
Yeah, it's going to be amazing.
Yeah.
So thank you for joining us on this deep dive.
It's been a pleasure.